Hello everyone, we are doing Lab 2 today, finding angle between two polar curves, curvature and radius of curvature. So here we are using again Python to find angle between two polar curves and to find radius of curvature. So basically angle between radius vector and tangent. In this we will discuss regarding polar coordinates, tangent to a curve, and angle between radius vector and tangent. So basically, polar coordinate means so in polar coordinates, point is represented by its distance from the origin, that is radius r, and the angle it makes with the positive x-axis theta. And tangent to a curve is represented like this. So that is the tangent to a curve at a point is a straight line that just touches the curve at that point, this point. And angle between radius vector and tangent is the angle between the line connecting the origin to a point on the curve and the tangent to the curve at that point. So the formula tan pi here. So this formula tan pi equals to r into d theta by dr is where the r is the radial distance of the point on the curve, and d theta by dr the derivative of theta with respect to r. And angle between two polar curves, this if tan pi 1 and tan pi 2 are the angles between the radius vector and the tangent of two curves at their intersection point, then pi 1 minus pi 2 is the angle between two curves at that intersection point. So this program to find the angle between the curves, r equals to 4 of 1 plus cos t and r equals to 5 of 1 minus cos t. So here the first line in this program, if I zoom in, you can see the first line from simpy import. So this line imports the simpy library, which is a Python library for symbolic mathematics. And this line is to define two symbolic variables, r and t, which will be used to represent the polar coordinates. And these two lines basically here we define the two polar curves, r1 a cardioid with a maximum radius of 8, and r2 another cardioid with a maximum radius of 10. And so these two lines here, the diff function is used to calculate the derivatives of r1 and r2 with respect to t. So these derivatives will be used to find the slopes of the tangent lines to the curves and the points of intersection. And finding points of intersection, the solve function is used to find the values of t where the two curves intersect. So this is done by solving the equation r1 equals to r2. And calculating slopes at intersection points. So these t1 equals to r1 by dr1 and t2 equals to r2 by dr2 and w1, w2. So the slopes of the tangent lines at the intersection points are calculated using the formula tan theta equals to dr by dt. And the subs function, this function is used to substitute the value of t at the intersection point into the expression for t1 and t2. and finding the angle between curves y1 and y2 and w and print. So the a tan function is used to find the angles whose tangents are w1 and w2. So the absolute difference between these angles gives the angle between the two curves at the intersection point. So basically, this code effectively demonstrates how to use uh, SimPhi to perform symbolic calculations and find the angle between two polar curves at their intersection point. So if I execute the same program in Python, okay, if I run this program, we can see the output is angle between curves in radians is 1.571. Okay, so which indicates that the angle between the two polar curves at their intersection point is approximately pi by 2 radians or 90 degrees. Okay, so this makes sense given the nature of the two cardioid curves. They intersect at 2 points, and at each intersection point, the tangent lines to the curves are perpendicular to each other. So this results in a 90-degree angle between the curves. And second one is to find the radius of curvature, and the formula to calculate the radius of curvature in polar form is rho equals to this particular formula, and where r is the radial distance from the origin to a point on the curve, and r1 is the first derivative of r with respect to the angle theta, and r2 is the second derivative of r with respect to theta. So this formula provides a way to quantify the curvature of a curve at a specific point in polar coordinates. So a larger radius of curvature, uh, so if this value is more, indicates a less curved curve at that point, while a smaller radius of curvature indicates a more sharply curved curve. And coming to program, so the first line, as usual, this line imports the SimPhi library, so which is a Python library for symbolic mathematics, and it allows us to work with symbolic expressions and perform symbolic computations. And t equals to symbol of t and r equals to symbol of r. So here we define two symbolic variables, t to represent angle and r to represent the radial distance in polar coordinates. And r equals to 4 into 1 plus cos of t. So this line defines the polar curve, r equals to 4 of 1 plus cos of t. And r1 and r2. So r1 calculates the first derivative of r with respect to t, and r2 calculates the second derivative of r with respect to t. Calculate the radius of curvature, where r is the radial distance and r1 is the first derivative and r2 is the second derivative. And this line, substituting the value of t, so this line substitutes t equals to pi by 2 into the expression for a rho to find the radius of curvature at that specific point. And this line basically prints the calculated radius of curvature to 4 decimal places. So by executing this particular code, you'll get the radius of curvature for the given polar curve at the specified point. So once you execute this particular program, then you will get the output as the radius of curvature is 3.7712 units. So this is the calculated radius of curvature for the given polar curve. That is r equals to 4 of 1 plus cos of t at that point t equals to pi by 2.